Hey everybody, it's Mr. Carr again. Today we're going to be looking at 12.1 day 1. We're going to be talking about limits again. It's been a little bit, but we're going to be talking about what happens when we estimate limits of functions at fixed values. Okay, so what that means is, if you kind of recall what a limit is talking about a unique value L that x is that the function f of x approaches. Okay, the keyword here is approaches as x approaches some value of c from each side. Okay, so for example, on here, we look at this position right here, that's going to call that L. So as x is approaching c, we're getting closer from the left side and getting closer to the right side. My graph is getting closer and closer here. So the limit is at L is the idea. Okay, so as the limit as x approaches c, f of x is equal to L, which means the limit of f of x as x approaches c is L. So that's what we're looking at here. So we're going to start with looking at a few examples. First one's going to be straightforward, is a linear function. So the key here, let's just graph that real quick. So 4x plus 1. So it starts here and I go 1, 2, 3, 4 up to the right, 1, 2, 3, 4 down to the left. So this is my function here. Okay. Now, one of the things that might help to understand is what happens as it says as x approaches -7. So we have a table here to help demonstrate that, but my graph does not go that far. So if I look at this, if I do 4 times -7 plus 1, that's a -28 plus 1, which is a -27. So I know that it equals -27 here. To help demonstrate this a little further, I'm going to go to Desmos just so we can see this as well. So here's my graph of that one. So if I go to -7, it's going to be way down here. You can kind of see what's happening. This is actually a good demonstration of what happens. From the right side here of this graph, I get closer and closer and closer to -7. Look at what happens to my y values. Okay, it's getting closer to some number. So I'm going to show that with a table here. So let me just delete some of these out. Okay, so I'm going to put, let's see here, put -7 right here. Okay, below -7 are values that are close. So for example, it'd be like -7.1, let's say. You see how it's negative 27.4. If I do -7.01, we got a little bit closer to my -27. When I go here, I go -7.001. Again, we're getting very close here. Look at my y column. It's getting closer and closer and closer to -27. Well, let me go the other direction. Oops. Yeah, right there. So if I do the same thing on the other side of -7, so these are going to be values that are greater than that. So for example, -6.9, we get that value. We get a little bit closer, -6.99. Got a little bit closer there. And if I go even further, -6.999, we see that is again getting close to -27. So my table, if I see that right there, from both directions, right here and above and below, we are getting close to -27. So again, it was -7.1, -7.01, -7.001, -27.4, -27.04, -27.004. From the other side, -6.9 was a -26.6. -6.99 was at -26.96. And then -6.999 was a -26.996. Again, the key here is that as we approach from both directions, we are getting closer and closer to -27. So what that means is the limit as x approaches -7 of 4x plus 1 just equals -27. That's it. Now, sometimes we have a little bit of interesting things that happen here. For example, x squared minus 16 over x minus 4. So when I do this, I'm actually going to go, if I plug in x is, for example, x is approaching 4, then I'm going to plug in 4 squared minus 16 over 4 minus 4, which is 16 minus 16 over 0. But here I come across an issue. Can't divide by 0, so this is undefined. So if I go to my table, 4 is undefined. This does not necessarily stop our limits, though. Our goal is to figure out, are we approaching a certain value? Okay, so let's go back to my Desmos real quick. Oh, come on. There we go. Turn this one off. So let's go to this one right here. Okay, So we're looking at approaching 4. And as you can see, we are getting closer to 4. And then we get this moment that's undefined, but then it's continuing on. So we see how the graph exists everywhere else except for that one moment. So we can do that, and we show this on here like that, okay? We're actually getting like a linear function, except for that one spot. So let me graph that real quick. So that is happening at 1, 2, 3, 4. It happens here. It goes, it's going to go this way, open circle, and then keeps going on like that. So my graph will look like this. Okay. So what's important here is understanding what are we approaching. So from the table, I'm going to go ahead and just write my numbers in here. But if I go from the low end, I'm at 3.9, 3.99, 3.999. The upper end, I'll go 4.1, 4.01, and 4.001. Watch what happens with our numbers. This is going to come to 7.9, 7.99, 7.999. This one is 8.1, 8.01, 8.001. Notice again, we are getting close and close to a number as we get towards this undefined spot. And that's okay in terms of limits. My graph is approaching from this way and approaching from this way. I'm getting closer and closer to a certain value. That value seems to be 8. So that means that the limit as x approaches 4, go up a little bit, of x squared minus 16 over x minus 4 equals 8. Even though the graph cannot actually cross at that point, it's still the limit is approaching it, and that's the important point. Okay, so, and that leads us to our idea here. We can have, okay, sorry about that. So we're looking at these 3 different cases here where the limit exists based on a variety of things. Now, notice again, in this hit, we just did an example like this. If there's a hole in the graph, the limit still exists at that value of L, okay? Because the idea is the graph is approaching it from both directions. Even though it doesn't exist at that moment, the limit does exist there. Even if I am defined at a different point, if I have this jump discontinuity like this, that's okay still, that's okay too, because what happens is we're still approaching a number. It's still going to be L, even though that GFC is defined at N. Then the last thing here is, if it's continuous, well, that makes sense. That was like our first example. It's approaching the same value. It just happens to be a value that is defined in this case. All right. So that leads me to talking about left-hand and right-hand limits. So when we talk about left-hand and right-hand limits, we are notating them a little bit differently. So when I say x approaches c with a little negative sign there, that is saying that I'm approaching it from the left. That's what that means. When I have a little positive symbol after the number, what I'm reading that as is the limit of f of x as x approaches c from the right. Okay, so we talk about one-sided limits, and we talk about the existence of an overall limit. That happens when this is the case. If the left-hand limit equals the right-hand limit, they approach the same number L, that means my overall limit is at L. So what we're saying here is f of x approaches the same value from both directions. Okay, as long as it approaches the same thing from both directions, then we have an overall limit that exists. So far, that's what we had in both of our examples. For our last one, we're going to see something that doesn't quite do that. So if I go to my, let me just show the graph real quick here. We're going to be approaching as x approaches 1 from both the left hand and right hand, and then the overall. Okay, notice how in my piecewise function, 1 is my cutoff point. So let's take a quick look at how the graph looks just to compare. And that looks like this one here. Notice that at 1, if I go here, it's all of a sudden going to be, oh, it won't show for me. And it's supposed to be undefined at 1. Okay. But then from here, it's okay, because I go down here, then 1 is equal to 3. So if I model that on here, I've got a quadratic that's going to start here. Maybe at 1, -2 is going to has that hole, goes up, comes down, and then it goes down to 1, 2, 3, 4, 5 down here. So here's my quadratic for the first half, and my second half is a linear. So it goes +2, and then it's going up 1 to the right 1, like that, and so on. Okay, so there's my piecewise model. If I look at the left-hand side, okay, so I'll start with that one. We're going to look at that left hand and we're going to look at the fact that this is coming from here to here. We can see it graphically. It's approaching this value. If I label it as a point, that is 1, -2. It's approaching the value of -2. If I go to the table, we can see what happens with that one too. From 1, it's going, if I go 0.9, 0.99, 0.999, okay, I plug this in a calculator or I go to my table feature, it's going to be a -1.81, -1.98, -1.998. So you can see from the left-hand side, we are getting closer and closer to a -2. So what that means is the limit as x approaches 1 from the negative direct or 1 from the left hand of f of x equals a -2. When I look at the right-hand side, that's going to be this one right here. Notice how it's approaching a different value. This point is at 1, 3. In fact, because this is x is greater than or equal to 1, that is going to be the value at 1. It's going to be 3. But let's take a look at the behavior on the other side. So from the right-hand side, we've got 1.1, 1.01, 1.001. If I plug those in, I get 3.1, 3.01, and 3.001. Notice from here, I am approaching 3 from the right-hand side. So that means the limit as x approaches 1 from the right-hand side, f of x is going to equal to 3. I have two different values here. Because there are two different values, the overall limit, so the limit as x approaches 1 of f of x does not exist. We cannot say it has an overall limit because it has to be approaching the same value from both directions. So that's my final part here. So we've done the left-hand and right-hand limits, and we come out to the fact that the overall limit does not exist here. Okay. And that's it for day one. We'll go into more interesting looking functions with this in our next one. But the idea is that our overall looking at what is a limit and how do we determine if it exists and looking at it from left-hand and right-hand directions. All right. That's it for today. Take care, everyone.